This is section 1.3, exploring random processes. Again, take a minute to pause and look at the objectives here. We're going to start today with interpreting probability. So in this class, we're doing a very simple approach to probability. We're not learning all of our different formulas. Okay, all we have to do is be able to interpret it. So we're going to interpret probabilities as a long run proportion. So if I tell you the probability of getting a straight in a poker is 0.0039, or if you change it to percent, 0.39%, this means if we play thousands of games in poker, we can expect to get a straight about 0.39% of the time. Or I could tell you the probability of rolling a 4 on a normal die is 1/6. Now, if you want to change it to a proportion, so this would be a fraction. 1/6 is a fraction. If you want to change it to a proportion, then you just divide. So you do 1 divided by 6, and that gives you a proportion. And if you want to times by 100, then you can get to a percent of 16%. What that means, though, is if we roll a die thousands of times, we should expect to get a 4 about 0.166, or 16% of the time. Some vocabulary. A random process is a process that can be repeated a very large number of times. So it doesn't need to be a lot of times. We're talking usually thousands. Under identical conditions, so you have to keep doing the same thing. Outcomes are not known in advance, but the probability of particular outcomes can be predicted. And what that means to us is, let's say that I'm rolling the die again, and I might know that the chance of getting a 4 is 1/6. Okay, but I can't tell you what's going to happen the next time I roll a die. I can't even tell you what's going to happen the next 10 times I roll a die. I might get like 1 4 or 2 4s or 3 4s, or who knows what is going to happen. But I can tell you that if I do it thousands and thousands of times, then I should get a 4 about 1/6 of the time. Okay, so that's what I mean. Like, individual outcomes aren't known. We don't actually know what's going to happen to these individual outcomes, but I can tell you the probability of what should probably happen in the long run. Okay, and just our official definition of probability now is it is going to be that long run proportion of times the outcome occurs if that random process just keeps happening. And it says indefinitely here. That just means a very large number of times. Really, you just keep going theoretically under identical conditions. So for example, the probability of heads on a fair coin is 0.5. Okay. Now, flipping a coin is a random process. I don't know what's going to happen when I flip the coin. Okay, I can't tell you if it'll be heads or tails next, but I can tell you if I flip it many, many, many times, thousands of times, I should get heads about 50% of the time. Okay, so what does the probability of 0.5 mean? It means if I flip the coin thousands of times, I should get heads about 50% of the time, but I still can't tell you what will happen on my next flip. Okay, now let's say if you were to flip the coin 100 times, how many heads do you expect to get? Well, half of 100 is 50, so I'm going to expect to get about 50 heads. But do you think you'll get exactly 50 heads? Well, it turns out that's usually not how things work. We don't usually get exactly 50, like I might get 49 or I might get 54, but it should be somewhere kind of close to 50. So we're going to use a computer to simulate tossing a coin 100 times. You can click on the link or scan the QR code, okay, and it should bring you here. Okay, so we can tell it the probability of heads as 0.5. Okay, I'm going to ask it to flip the coin 100 times and flip it. Okay. This is, each dot is the proportion of heads as it flipped. So the very first time it flipped, it was heads, and so we were currently at 100%, or 1 as a proportion of heads. And then we got heads again, but then we got tails, so we dropped down to 0.66 for heads. Okay, and it just keeps going. So each of these dots represents the proportion of where we are based on the number of flips. So you can see in the beginning that we weren't at 50%, we were all the way up at 1, and then went down, and then it kind of goes back up, and then it goes down, and then up. And so my proportions are changing a lot in the beginning. So in the beginning, I can't predict what's happening. But by the time we get out to 100, where are we? Okay, by the time we get out to 100, we're at 51% heads, or 0.51. Okay, I could try this another time, though. Okay. Well, now I've gone out to 200 flips. So let's actually change it and reset, and let's just flip again. So at 100 this time, we ended up with 49% heads. You can see down here, the proportion of heads is 0.49. Again, I started off with like 100% heads, and then we kind of varied. Down here, we suddenly got more tails, so we were like under 50% heads. So in the beginning, we change a lot, but then we'll get closer and closer to 50%. Let's try again. So now we had 51% heads again. So after 3 tries, we still haven't ended up with exactly 50 heads. Let's come back to our notes. So here are 3 attempts that I did in advance so that you can keep them in your notes. So like attempt 1, I got 49% heads, and I got 53% heads, and I got 55% heads. Again, you never know. On these ones, we all started off with like tails first, and so we started like 0%. Okay, on the ones we did, we had heads first, and that's just completely random. So again, in the short run, so when we say short run in this class, and the person that writes the test, you'll see her use short run a lot. Okay, short run just means we haven't done it very much yet. So in the short run, our proportions of heads seems to change a lot. Like you might be down at 0%, or you might be up at 70%. It's changing a lot. We can't really predict what we're going to get. But by the time we get to 100 tosses, our results are usually pretty close to about 0.5. Okay, but even at 100 tosses, I'm getting fairly different results for each attempt. So we have like 0.49 or 0.53 or 0.55. Those are pretty different answers. So let's instead toss the coin more times to see what happens. So I went through and had it toss it 10,000 times, which took a little bit of time. So you can see on this one, like we started off at 100 because we got heads first, and then we kind of went down. This is probably close to 100 here, 200. But then by the time we get to 1,000, we're really close to that 0.5. And then we kind of go up and down just a little bit, but it's very minuscule. By the time you're getting out to 10,000, we are just right there on that 0.5. In fact, you can see it's 0.5015. We are so close to 0.5. And if I tried it again, we vary a bit in the short run. But by the time we get out to 10,000, so close, 0.4983. Or I even had it toss it 100,000 times. Okay, again, in the short run, it varies a lot. We're up here, we're down here. But by the time we get out to 100,000, you can't see any variation at all. And we're 0.49973 heads. We are so close to 0.5. So now my question to you is, if you wanted to estimate the correct probability of getting heads on a coin flip, so you know it's 0.5, but let's say it's something that you don't know in advance and we're having a computer simulated. How many times do you think you should toss the coin? Or even if you're not doing a computer simulating it, if you have an actual coin at home that you want to check to see what the proportion of heads is. How many times do you have to toss the coin? So based on what we've looked at here, when we looked at 100 attempts, we still changed a lot, 0.49, 0.53, 0.55. Notice even when, like, if you're just looking at the proportion, we would have been at like 0.49, then we're down to like 0.45, and then 0.44, and 0.43. Like, it's just changing a lot, right? You could say we could do it 10,000 times, but that might be overkill. It kind of seemed to stop changing back around like 1,000. Okay, so how do you know how many times to do something in this class? Well, if you truly want to estimate the correct probability, you should keep repeating until the proportion stops changing. So once you settle in around 0.5 and you're not changing anymore, that's when you know that you can stop. Okay. So in the short run, our results are unpredictable, but once we repeat a process thousands of times, we'll get closer and closer to the true probability. And the more times you repeat the process, the better. You should at least keep repeating until your results stop changing. So we often use simulations to estimate probabilities of things we don't know. So for example, in many board games like Settlers of Catan, you roll 2 dice and use the sum. So suppose we want to know what the probabilities of rolling different sums are. Okay, you could take a more advanced mathematical class and learn ways to calculate this. But there are also a lot of things that we don't have rules to calculate. So instead we use simulations. Okay. So what we can do is we could roll 2 dice and look at the sum and repeat that hundreds of times. But actually rolling them takes a lot of time. So let's use a computer to simulate rolling pairs of dice and looking at the sum. Okay, so if we go to this link, we can have it roll dice and tell us the sum. So every time we'll roll 2 dice. This is one that I created a while ago. So if I roll the dice once, let's look and see how many 7s we get. Apparently it is really slow today. Let me look at that. Okay, now it's working. So I rolled the dice once, okay, and I got a 9. So you can look here down the table. It says possible sums 2 up to 12. So roll the 9. The frequencies account. That's how many times I've done. So I rolled 1 9. And so the actual percentage of 9s that I got was 100. If I roll, okay, but we were looking at 7 specifically, just so we keep checking 7. So when I rolled a 7, so far 0 times. So we'd write at 1 roll, we have 0 7s. Okay, let's roll the dice a few more times. So, oh, now I got a 3, now I got a 12. So now I've rolled 5 times. Oh, we did actually get 1 7. So when we look at 7, we have 1 7, and so my actual percentage is 20%, but we're supposed to be writing down decimals, so we'll write 0.20. Okay. Now let's go a few more times so we can get up to 10. So every time I roll, I'm just getting different numbers, and you can see the histogram of what I rolled keeps changing. So now I still have 1, but out of 10 rolls, that makes it a percentage or proportion of 0.10. Okay. Now I want to do it up to 100 times. So I'll actually be 110, but that's close enough. Okay, you'll notice this red is what I'm actually rolling. Okay, so the red is what I'm actually rolling. You'll notice this in a little histogram. So the red is showing us what we're actually getting. Underneath it, you'll see these brown lines. Those are actually what the theoretical probabilities are that I know because I use the math to do it. Okay, and remember when we first started, our red bars were all over, but notice how they're getting closer and closer to what we thought were these theoretical percentages. Okay, but at 100, let's look at the 7. So we actually got 27s. That gave us a percentage of 18%. So as a proportion, we'll write that as 0.18. Interesting that we were at like 20%, then we dropped down to 10%, then we're back up to 18%. Okay, let's roll 1,000 times. Okay, oh, notice how close my actual percentages are to my theoretical percentages. Okay, at the 7, it looks like I'm at 15.68%. So 0.15. Okay. Now let's try 10,000 times at least. And it's okay if you're a few over because you don't want to restart. So now, ooh, I'm so close. My 7 is at 16.76%, so 0.1676. And now it's set up to 100,000 times, so I will pause this for you. Okay, so I've now had it roll 100,000 times, over 100,000 times. Notice all of my simulated probabilities, okay, or percentages, are exactly on to what the math said that they should be. Okay, those histograms just line up beautifully. Okay, now if I go to the 7, it said I rolled at 16.74% of the time, so 0.1674. Now, last time we said 0.1676. Notice very close. I feel like we've stopped changing. Okay. I feel like we really know what the true probability is here. So what do you think the true probability of rolling a 7 is on 2 dice? Well, I would say I think it's about 16.7%. I feel very confident that we've really narrowed down to that 16.7%. What do you think the true probability is of rolling a 2? So I would come back to my chart, look at the 2. What was my actual percentage? I'm going to say that 2.72%. That seems to be pretty accurate. Now, what do you notice about the shape of the different possible sums? So if we look over here at my histogram again, what was the shape of that? I would say it is, I'm going to make this bigger again now. It's definitely symmetric. And it was even like almost normal. It wasn't quite normal, but that was actually just because we only had like 11 options. Okay. If we'd had more options, it would have looked exactly normal, but it was symmetric. It started to kind of look like a bell shape, but not quite. Okay. Now, these are just all those images of what we already did so that you can remember what it looked like for later when you study your notes. Okay. Again, what we actually get on our simulations changes a lot in the short run. So even by 100 rolls, we're not quite where we expect to be, but by 1,000 rolls, we're fairly close. 10,000 or 100,000, we're doing really good. So for this class, we should always simulate at least 1,000 attempts. Okay. So the person in charge of the test, she says 1,000. I like to do everything out to 10,000 just because I realize at 1,000 things are still changing a bit. Okay, by the time you get to 10,000, we're really good. However, for the homework and even exams, 1,000 is probably fine. If you're putting something into the computer and it's telling you that your answer is wrong and you think you did it right, maybe just try 10,000, because at 1,000 you might have still just been like slightly off of what we got, because we did 1,000 times, you did 1,000 times, we might be slightly off. So if you're having issues, try 10,000, but at least 1,000 for everything in this class. Now, one of the interesting things about this textbook is that they like to do simulations. So we're going to be doing simulations for the entire semester. Okay. But they found when they teach students that if we just have you go straight to the computers, you don't really understand what's happening. But if we help you use physical devices to do simulations, then you understand what's happening much better. Now, we're not actually going to take the time to do these simulations physically, okay, because this is an online class and I can't actually give you a pack of cards in class to do this. Okay? So I want you to instead just imagine how you can use physical devices to help you visualize what's happening. So for example, let's say we have a baseball team A that's better than team B and they have a 2/3 probability of winning on any given game. So what does it mean to say that team A has a 2/3 probability of winning? So remember, what's our definition probability in this class? It means if they play thousands of games, team A will win about 2/3 of the games. We can't tell you what will happen on the next round. Okay, we can't even tell you what will happen in the next 5 rounds, but we can tell you if you play thousands of games, they should win about 2/3 of them. Okay. Let's see. So if team A plays for team B for 3 games, is team A guaranteed to win exactly twice? Okay. Well, definitely not, for 2 reasons here. Okay. No. 3 games is really short term. Like, we can't really tell you what's going to happen with 3 games anyways. We can only tell you what happens for thousands of games. Let's see, probability only applies for like thousands of games, not 3. Okay, but also probability is never exact anyways. Okay, remember, even when we did 100,000 coin tosses, we weren't exactly at 0.5. We were still a little bit off. Okay, we can only tell you about. Okay, and we can't be exact. Okay, it's never going to be exactly. Let's see. So how could we simulate one game and whether team A wins? So there's a few different ways we can do this. We can use a spinner with a 2/3 chance to win and a 1/3 chances. So people would do a lot before we had computers. They would actually just like build a spinner. And so you could have like 1/3 is lose and 2/3 is win. And you just spin and keep track of which one it landed on. Okay. Or if you want to roll a 6-sided die, well, on the die you have the numbers 1, 2, 3, 4, 5, and 6. So if you need a 2/3 chance to win, then you'd find 2/3 of the numbers and say that's win, and you'd find 2 numbers and say that's lose. And you can roll the die and keep track of whether they won or lost. Okay. Or you could use physical cards, like you could write win on 2 cards and lose on 1 card. Then you could shuffle and draw a card, look at it, then put it back in, shuffle, draw a card. And you can just do that thousands of times. Okay. Oh, sorry. It says we want to simulate 1 game. So you would just do it 1 time. Okay. But what if we wanted to see what happens if they play 30 times and we want to count how many times they win? For us, this is a bit more difficult to find using our probability rules. Possible, but more difficult. Okay. So it'd be easier to just simulate it. So what we're going to do is we're going to use all these simulations up here, but we could use the spinner 30 times and count how many times they won. Or we could roll the die 30 times, or shuffle and draw the card 30 times. Okay? And then for each of those, we're going to count the successes, or the wins, out of 30 times. And that's how we can simulate it. Now, we don't like to actually do anything like this by hand. So we're going to go back to our ISI applets. When you scan the QR code, it will bring you back here. Okay. We need to go to categorical, and we need to find 1 proportion. Now, we can use coins or spinners. Spinners make sense because it's not 50%. I'm going to make my probability 0.66. Oops. 66666. Or however many sixes you want to put in, because it's 2/3. We want to play 30 times. So we need to spin this 30 times. And so I can do that once. So the pi stands for probability of success is 2/3. My sample size n is 30 because I want to do whatever I'm doing 30 times. And I can ask it to do that. So it's going to spin these spinners 30 times. So you can see it's spinning all the spinners. Okay. It said 21 times that I won, 9 times that I lost. And I put a little dot there at 21 wins. Let's take off the animation, make it a little bit faster. And let's draw a sample again. Well, this time we actually only had 13 wins and 17 losses. Interesting. Okay, so coming back to our notes for just a minute. So if lots of different people all ran a simulation of 30 games, do you think they'd all get the same answer? Well, I just did it twice, and I got different answers both times. So the answer here would be no. Every time we play the set of 30 games, we're all going to get different answers. But now I'm going to start asking you some things like chances. We'll have to have the side by side with our applet. Well, so we could keep drawing samples. So the next time I got 17 wins. And then I got 24 wins. Then I got 21 wins, 22 wins. So you can just watch every time I add a new dot. So every time I add a new dot, I'm getting a different number of wins. So like we got some 22s, we got 19s. This is going to take a little while, and so far I can't really tell you how many wins they should be getting out of 30 games. So maybe we should draw a few more samples at a time. So like now it'll draw 10 different samples. So now there's 10 different dots on here. Every time represents a set of 30 games. And I could keep going. So there's another set of 30 games. Notice we seem to have a lot around like 21 wins. Just keep going. So I have a few all the way down to 12. I have some up at 25. And I seem to keep changing a lot. Maybe we should do a few more sets of 30 at a time. So we can do 100 sets of 30 at a time. Interesting. It looks like we're kind of getting a more consistent shape here. Maybe we should try like 1,000. Okay, so now I have this nice histogram of how many wins I'm getting. So maybe go all the way up until I'm at like 10,000. So you can see right here, it'll tell me so far I've done 5,000 samples. So let's just keep going. Oh, now I'm over 12,000 samples. So whatever I've got is probably fairly good. Okay, so we've switched from dots to histograms just because there's 10,000 different dots on here. And you can see different things like the max we've ever gone was 29. Wow, they managed to win 29 ones. Or all the way down to they only won 11. But overall, they seem to really be around this 20, which makes sense. 20 is 2/3 of 30. So we can go through now and find the probability as how many times we got that outcome. And it will actually count for me, which is really nice. So you can push this button to change. Do you want them greater than, less than, equal to? So I can say, well, like, how many times did you win 16 games? And I can count. So 16 games happened about 4.5% of the time. Or maybe I want to know how many times did they win 20 games? And I can count. Okay, so it will actually right here, so the proportion of samples that had 20 wins was this 2,000 over 13,000 or 0.15. Or it will tell me over here on my histogram. Okay, so now let's look back at what it asked me to find. So what is the chance that they win the majority of the games? So if they play 30 times, the majority would be like 16 or more. Okay, so if I want to know if they win the majority, 16 or more, I can put 16 in here, and I can change my sign to a greater than or equal to. Okay. And it will count for me. It shows me in red. This is everything that was 16 or more. So that's 95.42%. So 0.9542 or 95.42%. So there's like a 95% chance that they're going to win the majority of their games. That's actually really high. So you'd be really surprised if they don't win over half the games. Okay, what's the chance that they win all 30 games? Well, for that, let's ask it to count first again. So we'll do 30. We'll change it back to an equal because they just said 30. Notice it was actually 0 times. Out of 13,000 attempts here, there were 0 times that they won all 30 games. Okay. Let's see, part D, how many games would you expect them to win based on a 2/3 probability? Well, this one is just math, not using our simulation. So if I have a 2/3 probability and they play 30 times, I'll just do 2/3 times 30. That should give me 20. So I'd expect them to win about 20 times. Yeah, but now this next one says, what is the chance that they win exactly 20 out of 30 games? Well, let's have it counted up for us. So I still want equals 20 count. So it says 15.38%. Sorry, I'm in the habit of changing everything to percents from the last time I taught this class before we switched textbooks. You can leave it as a decimal. It doesn't have to be percent, but you should be comfortable with either one. Okay. So we expected them to win about 20, but they only win exactly 20 about 15% of the time. There's also a lot of times they won 19 or 21 games or 18 games. Okay. And so remember this on probability. We expect them to win about 20 games, but it's not going to be exact. Okay. Let's see, what is the chance that they win 15 games or less? So we just type in the 15. We change it to a less than or equal to. And it looks like this time it's 0.0458. So only about like a 4.5% chance that they would win 15 games or less. Let's see, our next one. Suppose baseball team A only won 15 out of the next 30 games. Would you start to be suspicious of the claim of a 2/3 chance to win? Would you still believe that 2/3 was a plausible value for their true chance of winning? So we told you that it was 2/3 chance of winning. But then if you find out they only won 15 out of 30 games, well, what was the chance of that? We just found that right here in part F. The chance that they win 15 games or less, that was only like 4.5%. So now if I tell you they actually only won 15 games, are you suspicious? Okay. That doesn't seem very likely to have happened. Under 2/3 chance of winning, there's only like a 4.5% chance that would happen. I'm starting to get kind of suspicious. So let's come back and make some notes here. Now this logic is very important. We're going to be using this logic for everything we do for the entire course. Okay? So we could say something like, well, if their chance of winning, sorry, I am a perfectionist, but it is really hard to type and speak at the same time. So if their chance of winning is 2/3, then there is only a 4.5% chance that they would win 15 games or less. Okay. We are going to say or less here because if you come back to your chart, if we were suspicious at 15 games, wouldn't you also be suspicious at 14 games? And you'd be suspicious at 13 games and suspicious at 12 games. So when we talk about whether or not we're suspicious or something's plausible, we always start at the number we're at and go off into the tails, because if 15 is suspicious, 12 is even more suspicious, and 1 would be even more suspicious. So we count everything in the tails. Let's see. So there's only 4.5% chance that they would win 15 games if their chance of winning is 2/3. Okay. So if they actually only win 15 games, that is suspicious. Maybe 2/3 isn't their real chance of winning. And just remark, if they play thousands of times, we expect them to win close about 2/3 games, but it's usually unlikely to get exactly 2/3, just because there's always variability. And anytime there's random chance, there's variability in our results. So we like to run our simulations thousands of times to figure out what the different possibilities are. So now here's an example that seems similar, but we're going to use it to answer a question that would be important. So two baseball teams, A and B, are ready to play in championship. Team A is better and has a 2/3 chance of winning on any given game. So if you were on Team A, would you rather play one championship game or play the best out of 5 games championship? Okay, so this question, very important to people who plan things like the NBA finals, okay, any championship style. They need to know, like, how do these probabilities change when you play more games? Okay. Well, how would you figure this out? You don't know the probability rules to actually find each probability exactly, but we do know how to use simulations. Okay. So if we were to play one championship game, the probability of winning is just 2/3. They just said the chance of winning is 2/3. But how could you find the probability of winning at least 3 out of 5 games? So 3 out of 5, because if you're playing a championship, you have to beat them, right? You have to have the majority, so that would be 3 out of 5 games. Where in each game, Team A has a 0.66 chance to win. So we're going to simulate it. So we'll let each individual game be represented by a spinner with a 2/3 chance of success. So we're going to go back to our same applet. Okay, and we're going to ask the applet to spin 5 times. So this would represent one set of a 5-game championship. But if we just do it once, who knows what we're going to get? Okay, so I'm coming back to it. Our probability was still set at 2/3, but now we're only playing 5 games at a time. So we only need to go up to 5. And I don't want that yet. Just want one sample. So I could draw my sample. So this is like one championship modeled. Oh, this time they won 4 out of 5 games. But if they played another set of 5 games, do you think it's going to be exactly the same? So like, let's try again. Oh, this time we only had 3. Okay, and I can keep going. This time we had 4 again. Then we got 5. Then we got 2. But these are all very random. We want to figure out like what would actually happen over thousands of times. So we ask the applet to do it 10,000 times. And we draw the samples. So now you can see if we do it 10,000 times, then my most likely values are they'll win 3 or 4 games. Okay, they might only win 2 games, they might only win 5 games. Okay, just an interesting distribution that we have here. So now we can ask the applet to count the number of times we got samples as extreme as 3, because we have to win 3 or more to actually win this championship. So let's count. We want greater than or equal to 3, because we have to have 3 or more to win. So it looks like that happened about 79.5% of the time. So 0.79. So that's their chance of winning at least 3 out of 5 games. So which scenario would Team A prefer? Should they try just one game where they have a 2/3 chance of winning, or should they try 5 games where they have a 0.79 chance of winning? Okay. So obviously they're going to like 3 out of 5 games. So playing 5 games gives them a higher chance to win. So the better team is always going to want to play more games because the odds are going to be in their favor. Okay, they're more likely to, if let's say they're unlucky on one game, they can probably make up for it in their other games because they're just better overall. But Team B, who's not as good, they want to actually only play one game because maybe they'll get really lucky and win that one game. But it's a much smaller chance that they'll get lucky 3 games in a row to actually win 3 out of the 5 games. Okay, last example today. A game at a casino has a 0.5 chance to win. So how could you conduct a simulation to estimate the probability of winning at least 6 out of 10 times? So we want to know if we play 10 games at a time, what's the chance we win at least 6 of them? So we could flip a fair coin 10 times. Okay, actually, that's another question. So we could flip a fair coin, or we could shuffle a blue and red card. We draw one time. Blue means you win, red means you lose. You could use a spinner with a 50% chance of success. So you just have your spinner and it'd be split down the middle. Okay, you could roll a 6-sided die. You could win on the numbers 1 through 3 because that would be half of the numbers. Okay. But regardless of the method you choose, if you want to estimate the probability of winning at least 6 out of 10 times, how many times do you need to flip, draw, spin, or roll for the simulation? So if you want 6 out of 10 times, you need to do it 10 times. Okay. And then you need to count the number of attempts that have 6 or more successes. So we're going to use our applets, go to our one proportion. You'll see here that I told you we can use the coin, or you could use the spinner, but we'll use the coin. Probability of success is going to be 0.5. My sample size is 10 because each time I'm doing 10 things at a time. I need to put in thousands of samples, and I'm going to count my samples as extreme as 6 or more. And then we'll find what's the probability of winning at least 6 out of 10 times. So we can go back to using our coins because it's 50-50. Of course, if you use the spinners, nothing bad's going to happen, and maybe we'll just leave it there because it doesn't want to change for me. So we'll do 0.5. My sample size is 10 because every time I'm doing 10 things at a time, and let's just say 10,000 samples. Draw my samples, and I want it to be as extreme as 6 or more successes, and I count here. So here's my 6 successes or more. Looks like I'm at 0.3733. So 0.3733, or about 37%. So about a third chance that you'll win at least 6 out of 10 times. Coming back to the simulation, I want to show you a couple things. Notice here it says choose statistic. I can do my number of successes or the proportion of successes. So we wanted to count like 6 or more wins. You could think about it as the proportion of times that you win. So if I clicked on that instead, it will magically change everything for me. So it's centered right here at like 0.5. Because remember, our probability of success is 0.5. So you would expect to get about like 0.5, and instead of 6 out of 10 successes, it would be like 0.6. We'll use that more later in the class. Let's see, so we found that probability. Now your friend claims to have found a way to beat the system. He plays and wins 6 out of 10 times. Does this convince you that his claim is true? Well, let's write some notes here for ourselves. So if the chance of winning is 0.5, then there is a 37.33% chance that someone can win 6 or more times. Okay, so does it seem unusual for your friend to have won 6 out of 10 times? I mean, I would think that was actually fairly likely. There's a 37% chance that he can win 6 or more times. So it doesn't seem unlikely at all. So him winning 6 times does not seem unlikely or suspicious at all. Okay. So 0.5 does seem plausible as the true chance. So he tells you 1 6 times, you're like, oh, yeah, that's completely likely under a 50% chance of winning. Like, I'm not suspicious at all. I don't really think that you can beat the system. Okay, so I don't think he's found a way to beat the system. Now, let's suppose instead he played 100 times and he won 60 out of those 100 times. Would this convince you his claim is true? Well, it's still like 60 out of 100. That seems similar to 6 out of 10. But the difference is he played more times, so we have to rerun our simulation. So coming back to our simulation, now instead of 10 times, we want to do 100 times at a time. Okay. So it's shown me if we do 100 times, we should be centered around like 50%. Okay. We want to count what's the chance of him getting 60 or more. So 60 or more, that's actually now only 2.86% or 0.0286. So in the simulation, we change to 100 times, and we can say there's only a 2.86% chance for him to win 60 or more times, okay, if the true chance of winning is 0.5. Okay, so if he actually wins 60 times, I'm starting to get kind of suspicious. I'm starting to think, well, maybe the chance of winning isn't 0.5. So him winning 60 times is suspicious. I think maybe the true chance of winning isn't 0.5. I'm starting to think like maybe we were wrong on that first assumption. Maybe it's actually higher than that because he did actually win 60 times. And let's just make ourselves a note that we had to change the simulation to 100 as the sample size to figure that out, just so you don't forget when you look at your notes later. So that is probability. You're just going to practice doing this on the homework over and over. Every time you just figure out what you need to put in the simulation, and then you'll get a probability out of it.